Then we talk about seeing, that is, the sensation of eyes. Whereas other animals rely primarily on hearing, smell, or touch to understand the world around them, human beings rely in large part on vision. A large part of our cerebral cortex is devoted to seeing, and we have substantial visual skills. Seeing begins when light falls on the eyes, initiating the process of transduction. Once this visual information reaches the visual cortex, it is processed by a variety of neurons that detect colors, shapes, and motions, and that create meaningful perceptions about the incoming stimuli. The air around us is filled with a sea of electromagnetic energy, pulses of energy waves that can carry information from place to place. So, the sensing eye and the perceiving visual cortex. The light enters the eye through the cornea, a clear covering that protects the eye and begins to focus the incoming light. Then the light passes through the pupil, a small opening in the center of the eye. The pupil is surrounded by the iris, the colored part of the eye that controls the size of pupil by constricting or dilating in response to light intensity. When we enter a dark movie theater or a sunny day, for instance, muscles in the iris open the pupil and more light is allowed to enter the eye. Complete adaptation to the dark may take up to 20 minutes. Now, what is all happening behind the pupil is a science of the eye. And behind the pupil is a lens, a structure that focuses the incoming light on the retina, the layer of tissue at the back of the eye that contains photoreceptor cells. As our eyes move forward or nearer objects to distant objects, a process known as visual accommodation occurs. Visual accommodation is the process of changing the curvature of the lens to keep the light entering the eye focused on the retina. Rays from the top of the image strike the bottom of the retina and vice versa, and rays from left side of the image strike the right part of the retina and vice versa, causing the image on the retina to be upside down and backward. Furthermore, the image projected on the retina is flat, and yet our final perception of the image will be three-dimensional. Accommodation is not always perfect, and in some cases the light that is hitting the retina is a bit out of focus. The retina contains layers of neurons specialized to respond to light. The retina, with its specialized cells, as light falls on it, it first activates receptor cells known as rods and cones. The activation of these cells then spread to the bipolar cells and then to the ganglion cells, which gather together and converge like the strands of a rope, forming the optic nerve. The optic nerve is a collection of millions of ganglion neurons that sends vast amounts of visual information via the thalamus to the brain. Now, as we know how the seeing works, we should also know how it is connected to the brain via the visual cortex. So the visual cortex is made up of specialized neurons that turn the sensations they receive from the optic nerve into meaningful images. Because there are no photoreceptor cells at the place where the optic nerve leaves the retina, a hole or blind spot in our vision is created. When both of our eyes are open, we don't experience a problem, because our eyes are constantly moving and one eye makes up for what the other eye misses. But the visual system is also designed to deal with this problem if only one eye is open. The visual cortex simply fills in the black hole in our vision and similar patterns from the surrounding areas, and we never notice the difference. The ability of the visual system to cope with the blind spot is another example of how sensation and perception work together to create meaningful experience. Now, perception is created in part through the simultaneous actions of thousands of feature detector neurons, specialized neurons located in the visual cortex that respond to the strength, angles, shapes, edges, and movements of the visual stimulus. The perceiving color. It has been estimated that the human visual system can detect and discriminate among 7 million color variations, but these variations are all created by the combinations of the three primary colors, red, green, and blue. The shade of a color known as hue is conveyed by the wavelength of a light that enters the eye. We see shorter wavelengths as more blue and longer wavelengths as more red, and we detect brightness from the intensity or the height of wave. Bigger or more intense waves are perceived as brighter. One example of opponent processing occurs in experience of an after image. If you stare at the flag with stripes and some stars with left side, then move your eyes to the blank area anywhere around it, we'll be able to see an after image. And it's a good example of how image is used in the visual sector. How do we perceive it? What is the perceiving form? One of the important processes required in vision is the perception of form. German psychologists in the 1930s and 1940s, including Max Wertheimer, 1880 to 1943, Kurt Kofka, and Wolfgang Kohler, argued that we create forms out of their component sensations based on the idea of the gestalt, a meaningful organized whole. The idea of the gestalt is that the whole is more than the sum of its parts. So, this was a great principle as and under the course of bio and psychology. Perceiving depth. Depth perception is the ability to perceive three-dimensional space and to accurately judge the distance. Without depth perception, we would not be able to drive a car, thread a needle, or simply navigate our own way around the supermarket. What is the perceiving motion? Many animals, including human beings, have very sophisticated perceptual skills that allow them to coordinate their own motion with the motion of moving objects in order to create a collision with that object. Bats and birds use this mechanism to catch up with prey, dogs use it to catch a frisbee, and humans use it to catch a moving football. The brain detects motion partly from the changing size of an image on the retina. Objects that look bigger are usually closer to us, and in the part from the relative brightness of objects. The beta effect and phi phenomena. In the beta effect, our eyes detect motion from a series of still images, each with the object in a different place. This is the fundamental mechanism of motion pictures, movies. In the phi phenomena, the perception of motion is based on the momentary hiding of an image. What about hearing? Like vision and all other senses, hearing begins with the transdiction. Sound waves that are collected by our ears are converted into neural impulses which are sent to the brain, where they are integrated with past experiences and interpreted as the sounds we experience. The human ear is sensitive to a wide range of sounds, ranging from the faint tick of a clock in a nearby room to the roar of a rock band at the nightclub. Just as the eye detects light waves, the ear detects sound waves. Vibrating objects such as the human vocal cords or guitar strings causes air molecules to bump into each other and produce sound waves which travel from their source as peaks and valleys, much like the ripples that expand outward when a stone is tossed into a pond. Unlike light waves, which can travel in a vacuum, sound waves are carried within mediums such as air, water, or metal, and it is the change in pressure associated with these mediums that the ear detects. The amplitude or height of the sound wave determines how much energy it contains and is perceived as loudness, the degree of sound volume. Audition begins in a pinna, the external and visible part of the ear, which is shaped like a funnel to draw in sound waves and guide them into the auditory canal. And at the end of the canal, the sound wave strikes the tightly stretched, highly sensitive membrane known as the tympanic membrane or eardrum, which vibrates with the waves. The resulting vibrations are relayed into the middle ear through three tiny bones known as ossicles, the hammer or malleus, anvil or incus, and stirrup or stapes to the cochlea, a snail-shaped liquid-filled tube in the inner ear. The vibrations cause the oval window, the membrane covering the opening of the cochlea, to vibrate, disturbing the fluid inside the cochlea. The movements of the fluid in the cochlea bend the hair cells of inner ear, much in the same way that a gust of wind bends over a wheat stalks in the field. Although loudness is directly determined by the number of hair cells that are vibrating, two different mechanisms are used to detect pitch. The frequency theory of hearing proposes that whatever the pitch of a sound wave, nerve impulse of a corresponding frequency will be sent to the auditory nerve. The place theory of hearing proposes that different areas of cochlea respond to different frequencies. Higher tones excite areas closer to the opening of the cochlea near the oval window. Lower tones excite areas near the narrow tip of the cochlea at the opposite end. Pitch is therefore determined in part by the area of the cochlea firing the most frequently used eardrum. Just as having two eyes in slightly different position allows us to perceive depth, so the fact that the ears are placed on either side of the head enables us to benefit from stereophonic or three-dimensional hearing. What is called as hearing loss? So it's very clear that it is associated with the ear and hearing. So more than 31 million Americans suffer from some kind of hearing impairment. Conductive hearing loss is caused by physical damage to the ear, such as to the eardrums or ossicles that reduce the ability of the ear to transfer vibrations from the outer ear to the inner ear. Sensory neural hearing loss, which is caused by damage to the cilia or the auditory nerve, is less common overall but frequently occurs with age. The cilia are extremely fragile, and by the time we are around 65 years old, we will have lost 40% of them, particularly those that respond to high pitched sounds. Prolonged exposure to loud sounds will eventually create sensorineural hearing loss as the cilia are damaged by the noise. People who constantly operate noisy machinery without using appropriate ear protection are at high risk of hearing loss, as are people who listen to loud music on their headphones and who engage in noisy hobbies such as hunting or motorcycling. Sounds that are 85 decibel or more can cause damage to hearing, particularly if you are exposed to them repeatedly. Sounds of more than 130 decibels are dangerous even if you are exposed to them infrequently. While conductive hearing loss can often be improved through hearing aids that amplify the sound, they are of little help to sensorineural hearing loss, but if the auditory nerve is still intact, a cochlear implant may be used.